Hello.
Hello. Okay, so it's not being filmed, it's being recorded.
I don't have permission.
Okay, then just don't talk.
Oh.
Perfect. Win-win. Okay, so 3.1, we're going to be working with position, velocity, and acceleration. So, is anybody in physics right now? One? Just one person. That's so disappointing.
It would be two. Okay.
I didn't know we had physics.
You didn't know you had physics?
We had physics last year.
Yeah, they didn't have physics for like 2 years.
That's because not enough people signed up. So if you sign up, then you can get more people. Okay. Anyway, position, velocity, and acceleration are directly related to the ability to find a derivative in the rates of change. Okay. So the very first function is our position. Okay. So for example, I always think of the falling object, right? So if I'm going to throw something into the air, it's going to come down. It's going to tell me at a specific time where exactly the function is, or the ball is. Okay. Let's say, for example, that we're working in feet. Okay. So my position function would tell me how high an object is off the ground. Okay. The velocity is simply the derivative of the position function. Okay. So velocity is the derivative of the position function. So you can say v of t is equal to, let's say position. For some reason they like to use s. I have no idea why they use s. Standard position, maybe. Anyways, you derive it.
And Josh Giardini to the office.
If I was working with feet for position, what would we label the velocity in? Does it help that we're working in units of time? Oh, that's not the right lesson. Time, like seconds, like how fast something is moving. Feet per second, there it is, feet per second. So velocity is measured in feet per second. Okay, or potentially meters per second, or miles per hour, depending on what you're working with. Okay, to find acceleration, you take the derivative of the velocity function. Okay, so our acceleration function, we can write this, is equal to the derivative of the velocity, or one might say it's the second derivative of the position function. Okay, can you tell me how we measure acceleration? Like what would we label it? Feet per second, good. Okay, so you might write that down so you remember that if you see something labeled feet per second, or feet per second squared, you know you're working with an acceleration. Okay, beyond that, this kind of should be cut in half if you asked me, but beyond that, the second part is kind of telling you, if you have an initial position, your starting time would be time 0. Okay, so hopefully that makes sense to you. Your initial position is where you start when the clock starts. Okay, your initial velocity, ditto. Your time would be 0, where you're starting at. Do you guys see these little notations right here? See that little sub-0? Right there? That always stands for initial. Okay, so a little subtext. Okay, so sometimes I've seen like h sub 0, so referencing height, initial height. Okay. Speed. Speed, this is a big one. Speed, they'll ask you the speed of something. Speed is the absolute value of velocity. Okay, so a velocity can be positive or negative, and the positive or negative will describe the direction that it's moving. Okay, so speed is just how fast it's moving. We don't care in which direction. Okay, displacement is found by finding your final position and then subtracting the original position. So where did you stop minus where did you start? Okay, and then your total distance is the total distance you traveled. Okay, so the total distance you traveled can be slightly different than displacement. And an example like would be, I don't know why I just thought of this, but let's say you're running lines for basketball, right? You're doing a suicide, right? So you go all the way down back, all the way down to the far end, you come back, and then you go to the free throw line and come back. So your total distance, you have to add all of the total distance together, as opposed to displacement would just be your 1 full court. Does that make sense? Oh, that was kind of a weird example, but what's that?
Yeah. So let's say,
Oh, I guess you would stop. Yeah, I guess depending on where you stopped at.
so if you stop at the end of the court, it'd be the length of the court.
Yeah.
If you stopped and started at the front.
From the beginning, it would be 0. Yeah, that's a good point. I didn't think of a suicide would end at. Yeah, you're right. Good point. There you go. Perfect example. Okay, so let's do a few examples, huh? So example 1, they start with an S of t. So what kind of function are we working with? A position. So this is some position of who knows what. We're going to find its velocity function and then the acceleration. So how do I go about finding the velocity? Derivative. Very good. So I'm just going to take the derivative, which is going to give me my velocity. Okay, and what is the derivative of t to the third plus t? 3t squared plus 1. Perfect. There's our velocity. Okay, and then to come up with the acceleration, what would I do? Take the derivative of that, right? So if I derive my velocity, that will give me my acceleration. So what's the derivative of 3t squared plus 1? 6t. 6t. Okay, so that's a very basic example. Let's do something. You like that one? Basics are good. Well, no, unfortunately we can't. Will that be on the test? I can't guarantee that one. Okay, so round 2, we now have a position function as s of t, and the idea is that this is an object moving along a horizontal line. Okay, so imagine basically if I was going to be the object, I'm just walking back and forth here in front of the room. Okay, so we'll start with oh, and it says that it's measured in feet. Okay, and our time is in seconds, so that will help us label this correctly. Okay, so what is the initial position of the object? How do we find initial position? Good. Perfect. When the t is equal to 0, we can find the initial position. So the initial position of our position function, if I plug 0 in, clearly is going to take me longer to write that than just give the answer. 24, and I need to label that correctly. 24 what? Feet, right? Okay, so this is going to initially start 24 feet from our starting point. You guys paying attention here? Will you put that phone away for me? Thank you. Okay, number 3, what is the velocity of the object at time 1? Okay, so how would I go about doing that? Good. First, I need to find my velocity function, which is the derivative. Good. So let's take the derivative of our position. What would the derivative be? 16 times 3? 48. T squared minus 36 times 2? 72t. And then derivative of 24 is 0. So now, how am I going to find how fast it's moving at time 1? Plug in 1, good. So if I plug 1, I don't know why I just wrote a 2 there. 48 times 1 squared minus 72. So anybody know what 48 minus 72 is? Negative 24. Close. How are we going to label this? If we're doing velocity, good, feet per second. Now, does it make sense to you what the negative is in reference to? How can we have a negative velocity? Okay, it's the direction that the particle is moving. Okay, so a positive velocity is going to be moving to the right, where a negative velocity is moving to the left. So it's moving to the left at 24 feet per second. Okay, tells us our direction. Okay, number 20, or not 24, geez. Number 4, what is the speed of the object at time 1? How do we find the speed? Nice, perfect. So to find speed, I'm simply going to take the absolute value of my velocity at time 1. Okay, so we just did that. The absolute value of negative 24 is 24. So it's just telling me how fast the object is moving. Okay. Slightly less descriptive. That's the only difference between velocity and speed. Okay, what is the acceleration of the object at time 1? How do we find acceleration? Good. Okay, so we're going to derive the velocity function. So I'm looking at question 3. What is the derivative of 48t squared? 96t, and then minus, and then 72t would be 72, good. So now at time 1, I'm just going to plug in 1, so 96 minus 72, 24. So we have 24, and then how would I label this? Feet per second per second. Okay, so that means that this object is increasing in speed by 24 feet every second. Okay, so it's getting faster, right? It's speeding up. When is the object at rest? How would we figure out when an object is at rest? 0 to what? Velocity, right? Velocity, so something being at rest means it's not moving, so we're talking about a velocity. So I would plug 0 in, set it equal to 0. We want to know when the velocity is 0. So our velocity is 0. We need to find our t. So I'm going back to my velocity equation and setting it equal to 0. So this is going to require, let's see, greatest common factor. What would my greatest common factor be? Yep, bigger than, less than 12. There it is. 8t, it is 8t. So what would be left over? Uh-oh, 6t minus 9. Was that hard? Okay, so two positions where the object is at rest. Okay, so at 0 and at, can I jump to 3/2? Everybody follow that? Okay, now what does that mean in terms of the scenario of this object moving back and forth in front of us? Okay, so for an object to come at rest, basically it's a potential for change of direction. Okay, so if I'm walking in a positive direction, at time 0, I might turn around and go the other way, or I might just stop and keep going. Okay, so potential for change of direction. Potential for change of direction, that's what I was trying to say. Blah, 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 blah. Okay, when is the object moving to the right? Okay, so which of our 3 things tells us something about the direction that the object is moving? The velocity, right? So specifically when the velocity is positive, okay? So we're looking for, let's use green, when the velocity is greater than 0, and not equal to, right? Because 0 would be stopped. Okay, so all I have to do is figure out when it's set equal to 0. So we found the two places where it stops. So you see where we're using number 6. Okay, what I'm going to do is what's called a number line test. And I'm going to use those two values and then decide if it's positive or negative between the intervals that don't include those numbers. Okay. So if I plug in a value into my velocity, so remember we're working with the velocity function, which was, what was it, the velocity function? Okay, so, or I could even use this factored version that actually might be a little easier to mentally do, since we have such giant numbers. If I plug in a number less than 0, give me a number less than 0. -1, that's a nice easy number. So if I plug in -1, will I get a positive or a negative value? Okay, so I get a positive in that interval. Okay, now I need a number that exists between 0 and 3/2. What's a number that exists between 0 and 3/2? 1. Okay, so if I plug 1 into my velocity, would I get a positive or a negative? Negative. Okay, and then I need a number that exists greater than 3/2. 2. So if I plug 2 in, would I get a positive or a negative? Positive, right? Because if I use the factored form, that 8 times 2 is going to be positive, and then 12 minus 9 is positive, so positive times positive, right? Okay, so this number line test is telling me that when time was less than 0, it was moving which direction? Backwards, right? So, well, not backwards, it's moving to the right. And between 0 and 3/2, it was moving to the left. Do you see where I'm getting this, the negative? And then when time was bigger than 1.5, it was moving back to the right. So in seconds, yep. So when was the object moving to the right? When t is greater than 3/2, and when t was less than 0. Okay, and now that makes question number 8 quite easy to answer. When was the object moving to the left? And we probably should label those seconds. Nice labeling, right? Sex. Okay. When is the velocity of an object equal to 54? How would I do that question? Yeah, right? Set the velocity equal to 54. That one is pretty literal. Let's go back to our standard form. It was 40. I would use standard because it's equal to 54. So we're going to have to subtract the 54 and do some quadratic equation stuff. If we were plugging in 0, then I would use the factor form. But any number other than 0, I wouldn't. So first step on solving a quadratic, set it equal to 0. Now, we can use our magical calculator, unless it specifically says not to, right? So I could solve that in my calculator. Do you guys want to go through and do that, or can I just go ahead and tell you what it would pop out? Practice it? Oh, you're just good with trusting me? Because we can practice it if you want practice. Okay, let's practice. It's always good to practice. If you can be pretty efficient at the Inspire, life is given to a little bit. So, it takes a second for mine to pop up. I can't remember which one it is. It's a big program. But we're just solving, right? So you're going to hit math. No, not math. Just kidding. You're going to hit menu, go down to algebra. Oh, move this up the way. Did you get it?
If I did, it's really ugly.
Yeah, it is an ugly one. Oh my gosh, look at how tiny that is. I can't even see it. View. Holy, zoom in a lot. Oh, that's better. Okay, so we hit zoom. We go to... No, we don't hit zoom. We hit... I keep saying the wrong words, you guys. We hit... First you go into the calculate. Then you hit menu. You go to algebra and we solve. We're going to say 0 equals... That's all I remember. 48x squared minus 72x. And did you know you can actually use a t on these? If you don't like x's, you can use their variables. And then make sure you comma x. That's the part you might forget. Okay, so it pops out an exact answer. If you want to get the decimal version, since we're working with time, that would be more efficient for us to use. You hit menu, and then you go to number, and the very first one is convert to a decimal, and then you just hit enter, and we'll use those two numbers instead. Everybody okay with that? Did you get it? Oh, yep, that gives you something very different. Yours popped out a decimal? Ooh, your mode must be set differently. What did we get? So we got negative 0.549. Remember, you always round to 3 decimal places? Did I tell you that? Okay. So 2 places where the velocity is equal to 54. All right, what is the displacement of the object between time 0 and time 2? How would I go about doing that? Yeah. So figure out their position at time 0 and time 2, and then we just subtract them, right? So time 0, I feel like we did that. Didn't we start that one already? It was 24, right? 24. And if I plug 2 into our position function, I don't remember what our position function is. Let's see, in this little peak. 16 minus 36t squared plus 24. So, anybody get a number for that? I got negative 16. No, I didn't. Just kidding. That's the final answer. I got... I have no idea what I got. Does anybody have it?
I got 8.
You got 8? Okay. 8, weird. What?
I'm working backwards on how you got 16.
I don't know. I'm actually looking at it going, what on earth did I do?
Well, because you said the final answer was 16 and you're starting with 24.
Oh.
So the middle answer would be...
I know, but I have like, it says 128 minus 144. Well, that's also negative. Yeah, I don't know what I did. Anyway. So, ooh, by the way, you got to start at your S of 2. So your final position minus your initial. Okay, so we have to do 8 minus 24. So we end up with negative 16 feet. So what is the reference of the negative? Yeah, so I started 16 feet left of where I started. So it tells us direction. Okay, now total distance. How am I going to figure out total distance? Okay, so this is going to be important. Any time that I stopped and then turned around, I have to know my position at those places. Okay, so we need to know our position at the start time and the finish time, and any time we stopped in between. right? Our downs and backs, right? When we stopped and turned around. Okay, so between 0 and 2, where were the two places that we stopped and turned around? Okay, so at 0, but we don't care about 0 because that's our starting time. But 3/2 is in the middle of our time. Okay, so we need to figure out what our position was at 3/2. Okay, so let's say our position at time 0 was 24. Our position at 3/2, we need to know that. Anybody get -3? That's what I got. Do you disagree or? Okay, perfect. Okay, so if those are our three positions, we basically need to find the total distance between the three positions. Okay, so if I was going to find the total distance between 24 and -3, what is the total distance there? 27. Okay, so we have 27 feet there, and then what's the total distance between -3 and 8? 11. So what is the total distance that we traveled? 38. Does that make sense? Okay. What's that? There's a lot to do for that one. Yeah. That one is, yeah. Okay, so this next little piece is kind of understanding a graph. Okay, so it says the graph shows the position function of a remote control car. I said that too many times. Remote control, okay, car. Answer these questions. So, was the car going faster at A or at B? Why? Because what? It shot up. Steeper slope, there it is. That was the word I was looking at. Okay, so A is kind of has this steep of a slope, so that's like, I don't know, 1-ish. And then at B, definitely a steeper slope. So the steeper slope, remember slope is telling you the rate of change, which is giving you a velocity, how fast something is moving. So good. B, and maybe you can write down because it has a steeper slope. Okay. When was the car stopped? Okay, and how do you know that? The slope didn't change. Okay, now, not that I'm disagreeing, but what if it was a straight line? A linear piece would have the slope is 0. There you go, perfect. So between C and D, because the slope is 0. Okay, big idea right there. When this, well, what happened is basically between C and D, it just like, so it went and then it literally stopped for a second. I don't know how long. And then it came back really fast. Like if it didn't stop for a second. Then it would still have a speed. So it'd still have a velocity. It would look, if it kept going at the exact same speed, it would look like a straight line with a slope of, let's just say it was traveling at 2 feet per second. The speed is constant, yes. So it has a slope of 2. You're thinking of like acceleration. It's speeding up versus slowing down is acceleration. Okay, but this is the position function. This is where the function is, where the car is at a specific time. Okay, at what point was the car's velocity the greatest? What? E and F? Is there one that seems steeper than the other? Okay. The answer to this is B. Exactly. Say that louder.
The velocity for E will be negative.
Okay, so velocity, remember, velocity, even though it's the greatest speed, velocity still has to mean, if we have the greatest, we're talking about the most positive number. So that is including a direction and a slope. So the one that has the greatest velocity is going to be at B, because it has to have a positive slope. What were you saying, Josh?
Physics.
Who? James? Greatest velocity always matched, just not reflected upon direction? Interesting. I might have a chat with her, so we're on the same page. Well, it could be different. I'm not saying that she's wrong. I'm not trying to say that she's wrong at all, but maybe you could have misinterpreted what she said. That's a possibility. I don't know. I should ask her, though, because then we can nail it down, right? So it's a good question. You should ask her and say, hey, give her this exact table and say, yeah. Okay, so because, what did we say? Has the greatest positive slope. Good. Positive slope. Okay, so now 15, which one has the greatest speed? Which one is moving the fastest regardless of direction? Okay, that one is going to be E. E. How can we say that? Has the greatest absolute value slope, though, right? How close are we? Oh, good, we're almost done. Nice. Okay, so vertical motion. Ooh, this is what I was talking about, the ball in the air. They love this position function. They love this idea. You see this over and over, and I think you've probably even seen it before this class.
On the test that
Oh, yeah. Yeah. Have you guys seen this equation before, negative 16? So, did I miss a part? They didn't give us the generic one? Okay, I'm just going to throw it in. I'm sure they'll give it to you at some point, but just for funsies. Position function of a falling object. Okay, and this is dependent upon if you're working in feet or meters. Okay, so if you're working in feet, your position function, anybody know? Josh? Oh, you don't know it off the top of your head? Oh, really? Oh, I'm kind of saddened by that. Not really, it's just saddened. Okay, let's see. Negative 16 t squared plus, anything come to mind? The initial velocity times time plus your initial height. Have you seen this before?
I've seen it. I remember it.
Yeah, they love this equation because it's, I mean, everything can be thrown into the air. Okay? So just so you know, remember that this is your initial velocity, right? If you didn't notice that already. And then that's your initial height. Well, the good news, Josh, is that you will have that memorized. Either for her or for me. Yeah, you will know that one. Okay, so the nice thing is that they gave us this equation of this, what do we got here? A ball. Naturally, you would throw a ball off a high cliff, because that is fun. I've probably threw a rock, but whatever. So can somebody tell me, how high is the cliff? 160 feet. What did we throw the ball at? What velocity? 48. And notice, it's a positive velocity. So what direction are we throwing the ball? Up. So we're throwing it up into the air as opposed to potentially throwing it downward. That would have a negative velocity. Right? Okay. Find the initial velocity. Oh my gosh, I'm just right on page here. Okay, so how do I find the initial velocity? Oh, I see why they didn't give you the... Yeah, so knowing that I just told you what everything is, we know that it's 48, right? So to prove it using calculus, how would we go about doing that? So we'd find the velocity. Yeah, so velocity is our derivative. So velocity would be negative 32 t plus 48. And then all we have to do is then plug time 0 in, because that's initial time. So therefore it was at 48. And how do we label initial velocity? Feet per second. Okay. At what time does the ball hit the ground? Okay. Tricky part here is, which function do I use? Okay, are we talking about a position? Are we talking about a velocity? Are we talking about an acceleration? When the ball hits the ground, which one is that? Well, not necessarily, no. We know when the ball hits the ground is when the height is 0. So we're going to use the position function for when. Okay, so when the ball hits the ground, well, I didn't mean to slide up on that, is all we're going to do is set our position equal to 0, because that's our height, right? Our height is equal to 0. Okay, so we get a quadratic equation to solve. Anybody feel okay with me? Actually, this one is factorable, but should I solve? Yeah, right? Can I go ahead and just tell you what it equals? I mean, we can do algebra if you want, but since we know how to solve, we're experts at solving quadratics, we got this. So when you solve that, you would get 5 and negative 3. Now, one of those makes sense and one of those does not. Okay, negative 3 makes no sense. We can't go back in time and throw a ball, right? That doesn't make sense. So it's only going to be time 5 seconds. Okay, last question. At what time does the ball reach its maximum height? Okay, what do you think about that one? Can I what? Like that, and just go like that? You could. But it would be way cooler if you use calculus. Because when you're talking about a max, Spencer, this is a really good idea. Max, what are you looking at? What's the slope at any max value? 0. So all we have to do is figure out what the derivative is and set it equal to 0. And we know when the max is. Okay, so if I take my velocity, set it equal to 0, we can solve that. That's pretty easy. So we get negative 48 equals Negative 32. Ooh, I don't know what that is. Wait, I wrote it down. 1 and infinity? How about 1 and 2? In fact, exactly halfway in between, actually. 1.5 is your exact amount of seconds. Okay, so that's it. What do you guys think? Isn't it kind of fun when you start to like use real world scenarios with math? Yeah. Yeah. Like these two worlds like majorly collide. It's pretty cool. I really liked physics. In fact, that was probably one of my favorite classes in college I took. Okay, so we have some minutes. Just some minutes. Just like 55-ish minutes. You guys want to start this together? Alright, it does say you can use a calculator for these questions. That is super exciting. That will make solving quadratics easy.
What is this?
Okay, you guys ready? Yeah, we got this. Piece of cake. There's only 18 problems. You're right. So it's just that the first 10 have like 8 involved. Not on every one. Like number 3 only has an A and B, so. No, I don't think so.
I'm pretty sure.
All right, you guys ready? Okay, so we have a position of a particle moving on a straight line. Okay. Notice it's a cubic function. Looks like a John Travolta if we were going to graph the position. Find the velocity function. Well, this is easy. Anybody know what our velocity function is? The derivative? Anybody get 12t squared plus 6? Or just me?
Maybe. You shall never know.
You don't have enough patience for this? Would it be better if we just called it 1, 2, 3, 4, 5, 6, 7, 8, 9, and then the next one? Okay. Find the velocity at time 2. Okay. Oh. Yes. Let's see. 4 times 12 is 48, plus 6 makes 54. Anybody else get 54? And then make sure you label feet per second. So I will tell you on this section, labelings can make or break you on your tests.
Make sure not to label.
So label everything.
Somewhere.
Meters? Oh. Ooh, good call. Oh my gosh, I would have lost like 5 points right there.
Labeling is everything.
Okay. You're right. Pause for 1 moment.
I said give Josh something.
Oh, I'm sorry, geez.
Everybody can't do it.
He deserves some cake. And I deserve some cake. Honestly, now.
Oh. That went like right through your hand. You might be right. You just kind of proved that. I'm definitely on your page. All right. C. Find the acceleration. How do you find the acceleration?
Yeah.
Anybody? Find the acceleration? Velocity, right? So, anybody get 24t? Thank you. Well, you guys were taking a long time.
Writing down the equation.
Okay, D, find the acceleration at time 3. What are we doing? Good, you plugged 3 in. And 24 times 3 is like 672, yeah. 72, how do you measure or label accelerations? Meters per second per second. Okay, E. When is the velocity of the particle 18 meters per second? What do I do? Set it equal to, because the velocity is 18, good. So 18 equals 12t squared plus 6. Let's see, we can solve that. Ooh, 12 equals 12t squared. So t is what? Close. Plus or minus 1. We do have to include negative times for this. Because. Since we're working with a particle on a straight line, we're going to include our negative time. But if you're working with like the position of a ball, then we wouldn't have a negative time. Wait, are we on F? Okay, yeah. So find the velocity when the position of the particle is 25. It's not super complicated, but set it equal 25 to the original. Why?
Because it's the position.
Okay, and what would we find? T, which would be what? The time when the particle is 25. So that would be our time of when. Once we have our time, we can then find our velocity. This is a two-part question. We first have to figure out when it's at 25 feet, or whatever we're at, 25 meters. Once we know when, we can then find its velocity. Okay, so 25 is equal to our position function. It's possible that there's more than one place, or time, I mean. Who's going to be our calculator for today? Whoever can type this in fastest. 1.5 seconds. Thank you, Jaden. Okay, so once I know when, now I can find the velocity. So now I can take the 1.5 and plug it into the velocity equation. And that equals anyone? We all got like 89 calculators sitting in front of you. What is it? 24 even? 24 meters. Oh, you got 33? Okay, let's see. 3 halves squared is 9 fourths. 9 fourths times 12 is 3. 3 plus 3? No, I did not do that right. What'd you get? 3. Hold on. That was really good mental math. That was like brain fart. Holy cow. 3 times, oh, see, 3 times 9. So then it would be 27 plus 6. 33. I got 33. Have you guys ever seen, I think it's like Friends with Benefits? Have you guys ever seen that? It's pretty good. And he's like trying to calculate how high he is, and he's like, wait, that was like just like that. Wait, that didn't even make sense. Well, he's like, they're sitting on They're like in where are they sitting on the sign of the Hollywood sign, and he's figuring out how many fences it would be. And he's like 3 fences, so that's like 100. Like he's way off, and he's like, wow, that's really high. You gotta see the movie. It's pretty funny. It's a great movie. One of my favorites. Anyway, find the initial position. How do I find initial position? T equals 0 of what? Which one? Initial position. So we're plugging, so T is going to equal 0 of our position. I don't know why I wrote it that way. Let's write it S of 0. Yeah, exactly. Plug in 0. Yes. Okay. Meters. Okay, and then H, find the particle's displacement from 0 to 1.5. So how do I do that?
Yes.
So initial displacement, I gotta figure out where my position is at time 0, and time 1.5, I have no idea what happens when you plug 1.5 in. Somebody's got to calculate it. Oh, good call. So 25, yeah? Jaden, you're so smart. Because that was up in question, which number was that? In F, or letter F. So then we have to do displacement. Start minus, so 2.5 minus 25. So we get negative 22.5 meters. How's that? Sound good? In question F, well, it's Jaden told me that when you solve it, it's 1.5. Oh, 1.7 for letter F. Can somebody verify F? We were getting 2 different answers for F. 25 equals. So yeah, it shouldn't change our answer H, but it would change our F. Oh, so what'd you get, 1.75? Equals, wait, you forgot to equal to, oh wait, you have, hold on, what did you do? 2, so minus 22, okay. So 1.737. 1.737. So that would make this, what do you say, 40? 42 point what? 226.
Changes it a little bit.
Yeah, I would say quite a bit. Did you get it? Because I would have typed it in as, and I can verify, I guess, since nobody else wants to. You got 1.5? Uh-oh. 25 equals. What comes after that? 4t?
Oh, you made it square.
Oh. So that'll be, okay. Nice. Okay, so we're okay. Good. I'm glad you figured that out. Good job. Good teamwork, guys.
But the 25 is the part right?
Yeah. Position, yeah. Okay. Number 2, all right. Already on number 2, guys. Number 2. Okay, so a helium balloon rises so that its height position is given by S of t, where height is measured in feet and time is in seconds. Assume that t can only be greater than 0. When is the balloon height 45 feet? How do we do A? Anybody else setting it? Good, thank you. So 45 equals t squared plus 3t plus 5. You got 5? 5? 5 seconds? Okay. B. How fast is the balloon rising at time 1? Okay. How fast is it rising is a velocity. Yep. So first we have to figure out what the velocity is. 2t plus 3, agreed. And how fast is it rising at 1 second? We'll throw that in. 5. Well, that's a new notification. Okay. Meters per second. What, Kirsten? Were you unconfused?
Yeah, I did.
Good, okay. How fast is the balloon rising at time 4? Okay. So plug 4 in. So 8 plus 3 is 11. D. What is the balloon's velocity when it's 45 feet high? Okay, how do I do that? Good, so we start with the position because we got to figure out when it's 45 before we can figure out its velocity. Oh, we already know. Oh, that's good. That was nice of them to give us a nice number. So all we have to do is plug 5 in, huh? So just to clarify, what is the difference between B and C and then D? How fast is the balloon going versus what is the velocity? What's the difference between those two questions? It's a speed question, okay, which means if we would have gotten a negative number, we would turn it positive and then it would tell us how fast. Oh yeah, we can just do this for the rest of the class period, unless you guys want to do it on your own.
No.
But it's
I'm still kind of once we get to the other stuff.
okay. Yeah, speed is just your velocity, which is positive. That's just it. Velocity just gives you slightly more information. Yeah. Okay. 3. Let's see. We have a ball rolling on an inclined plane. Ooh, I feel like we did this once before. With the position function of S of t, where the position is measured in centimeters and time is in seconds. Find the ball's velocity at time 2. Okay, that seems pretty straightforward. Do you guys agree? So find the velocity, then plug in 2. So I get velocity as 6t squared plus 6t. And if we plug in 2, uh, 24 plus 12 is 36 centimeters per second. When is the velocity of the ball 30 centimeters per second? So what's that one? Good, velocity equal to 30. 6t squared plus 6tu. I feel like that one's not too bad to solve actually. 5, 2, 3 to get negative 2 and negative 3. No, 2 and 3. 2. Help, help. Phone a friend. Because you can divide by 6. Oh, 5. So never mind. Yeah, it's not nice. What did you get? Super. Negative 2 point, what did you say? 791. 791 and positive 1.7. Okay. Do you remember the part where it says, was this problem? Oh, no, that was the last problem where t has to be positive. Four. Ooh, I like these graphics. The graph at the right shows the position function of a car. They like cars. Answer these questions and explain your answer. What was the car's initial position? What? Oh, sorry. Didn't hear you. 0. Is everybody okay with why it's 0? Do we have any units? 0. So initial position is at your time 0, right? So right when it starts. I feel like that's pretty self-explanatory, but yeah? No? Good? Okay. Was the car going faster at A? And notice it says faster. Not telling us about a direction. At A or at B? A. How come? Okay. C. Was the car speeding up or slowing down at B? How come? Cuz. Okay, so how do we know if something is slowing down? Speeding up or slowing down? The speed, okay, the speed is decreasing. So when you say speed is decreasing, thinking in terms of position, velocity, and acceleration, what are we talking about? In more time. Okay. Okay, so for something to be slowing down, we're talking about acceleration, right? The acceleration has to be decreasing. So we're basically talking about the slope of the slope. So what do you think is the... Let's see, let me think how you do this. Because the slope, it's almost horizontal. So the slope looks like it's, I don't know, let's just say 1/2. Slope is flatter. Kind of, yeah.
Could you say like the slope is approaching zero?
Oh, actually I like that. Yeah, because it was big and then it was approaching 0. I'm kind of interested in what they wrote. All right, what happened between C and D? Stopped. How do we know it stopped? Slope is 0, yeah. Just so you know, no slope would be a vertical line. Okay. I'm curious about that one. I'm gonna look it up. Hold on. Pause for a second. The slope is decreasing. Okay. All right, you guys ready for 5? All right, so 5, we have you guys with me? 5? Ready for 5? 5? I'll take that as a yes, I guess. All right, so we have a particle moving along a horizontal line, and it's measured in centimeters per minute this time. Find the particle's displacement between time 0 and time 5. Wow, they go big off the bat here. So how do I do 5A? Right, so initial and final position. So I'm looking for x of 0 will be 0, and x of 5 is 125 minus 75, so 75, right? So 0 minus 75, what? 120. Not today. Yeah, today.
Yes, it is.
Yeah. I was thinking, okay.
Not today.
Sorry, we're breaking down.
Oh, good lord. I'm officially losing
We
it.
got that on recording.
That's awesome. Yes, I'm still recording.
Oh, good.
I'm going to have to edit this recording. Oofta, okay. All right, find the particle's velocity when time t is 4 minutes. How do we do that?
Just plug in 4 into the velocity equation. See how it says it first.
Okay. 3t squared minus 6t. Plugging in 4. So what's 16 times 3? So 48 minus 24. 24. And we're working with a minute. All right, find the acceleration at t4. So acceleration is 6t minus 6. Plug in 4. Cut D. At what time does the particle change direction? Okay, how do we get the numbers for the number line? Well, we don't know if it's 0 or 5 for sure yet. So when it changes direction, there's a instant when the velocity is 0. Okay, so what we're going to do is we're going to take the velocity equation, set it equal to 0, and then we'll do our number line test. Okay, so 0 equals, what is our velocity? 3t minus 6t. So t minus 2, 0, and 2. Anybody else agree with that? Okay, so now on my number line, we have 0 and 2. Okay, so if I plug in, let's just say -1, I would have a negative times a negative. So a positive. Anybody else get a positive for -1? Okay, if I plug in, let's just say 1 between 0 and 2. Okay, negative. And what about between 2 and infinity? So if we plug 3, positive. So we can say, because it's moving from a positive to a negative and a negative to a positive, that it changes directions at 0 and 2, not seconds, minutes. Okay, so you have to show the number line to prove that it goes from a positive to a negative or a negative to a positive. Because it's possible that you would have kind of like a John Travolta effect. Like it levels, like it has a slope of 0, but then keeps going in the same direction. So, yes. You can make an educated guess, but just don't pick wrong. Alright, what is the total distance traveled by the particle between 0 and 5? So total distance, we have to know the displacement between 0 and 5, but we also need to know when it turned around, where it is when it turned around. So, the position at 0, the position at the place that turned around, so at time 2, if I plug 2 into our position, 8 minus 12. Okay, and then our position at time 5. I don't know if we ever figured this out. Did we? Oh yeah, how can I forget? It is 50. So, what's the displacement between 0 and 4? Or negative 4, I mean. Or the distance between, yeah, sorry. And then what's your distance between negative 4 and 50? 54. So your total distance traveled will be 58. What are we working in? Centimeters. Ooh, I feel like this next one is going to be rugged. Okay, so they immediately give us a little helper. So I would probably highlight that. You might want to keep that on your notes for whenever test is next. So average velocity. How fast something is moving on average. Average speed. Okay, notice they're found differently. So average velocity is your displacement over your time elapsed. Average speed is your total distance over your time elapsed. Huh, interesting. Okay, so, well, I don't know, I haven't read F yet. Okay, so find the particle's average velocity between 0 and 5. Okay, so, I feel like we found displacement already, didn't we? We did, right? So displacement between 0 and 5, that was from A. It was negative 50. And then our displacement for 5, 0 to 5 would be negative 5. Well, 0 and 5. Time elapsed 5. Time elapsed positive 5. So, negative 10. Average velocity, how do I label this? Centimeters, wow. So we're just doing velocity, centimeters per minute. So, average velocity is technically a slope formula, right? Because you have displacement, which is just a y2 minus a y1 over elapsed time, x1 minus x2. So average speed and average, an average rate of change. So, so G, what's our total distance? Did we figure that out? We figured that out before, didn't we? Total distance was 58 over our elapsed time. What's that? 58 divided by 5. 11 point, yeah. 11.6 centimeters per minute. Interesting. we're almost done with this. Yeah, but like 6 and 7, after that it's like quick stuff. Find the derivative. Find the derivative at a point. Find the second derivative. Find the equation of a tangent line. Find a point. Those are all reviewed quick questions. Piece of cake. We'll just call this number 6 right here. Actually, maybe I'll go to the problem. Okay. Number 6. The graph at the right shows the velocity. Ooh. So this is velocity. So how fast it's moving. Also notice that positive and negative is telling you the direction that the function is moving, right? So for A, when is the particle moving left? How do we know when the particle is moving left? When it's negative. Oh, and they gave us a super awesome. How are we going to find exactly where that x-intercept is? Huh. Just so you know, on a guess, it's 1/4. How'd you figure that out? Okay, so you're using the slope to figure it out. Okay, by the way, if you guessed and you made an inaccurate guess, that's how you lose points on a test. As long as you're right about the 1/4. Yeah, so 1/4 is less than t is less than 7? Okay. When is the particle's acceleration positive? Okay, so let's think about this for a second. What is the acceleration in terms of velocity? How do we go from velocity to acceleration? It's the slope. So we're just analyzing where on this graph does it have a positive slope? From 4 to 8. Yeah. So 4 to 8. Okay. When is the speed the greatest? Okay, so let's think about speed. How are we relating speed to velocity? Direction doesn't matter, right? So it's the absolute value of whatever your velocity is. So when do we have the greatest absolute value? Yeah, between 1 and 4, yeah. So that one's going to have a speed of 3, whatever we're talking about. So 1 to 4. And D, when does the particle stop? For more than an instant. So, okay, so now let's think about velocity. How do we know when something is stopped in terms of velocity? When what? Say that louder. When it's 0. Okay, so we are looking for where is the velocity 0 for more than an instant. Between 9 and 10, there you go. Good. C, okay. Oh, no, that's good, okay. No, not because the slope is 0. It's because it has the greatest absolute value of the velocity. So like the biggest y value in terms of that graph. Basically, you could think of it the furthest away from the x-axis, I guess.
And then the d divided because it's at 0.
The velocity is 0 for more than an instant, yeah. Not because it's the longest amount of time, just because it's for more than an instant, 1 second. Okay, we ready for 7? Or do you guys want to stop? We got 10 minutes. We can do 7. Okay, the position at time t seconds of a pebble dropped from initial height of 600 is s of t. So notice that for that question, what would the initial velocity be? For number 7, what's your initial velocity? The initial velocity would be 0 because, do you remember the equation that I gave to you? That one you wrote down, that middle term, there's no linear term. So it means that that's 0, which would make sense if I'm about to drop something. Right before I drop it, it has no velocity, right? Okay. At what time will the pebble hit the ground? See ya. So, hitting the ground, what are we talking about? What equal to 0? Position, good. So position, the height is 0 when it hits the ground. So 0 equals negative 16 t squared plus 600. And I don't know what that is. 6.124 seconds. Good. Okay, what is the pebble's velocity when it hits the ground? Never. That's my answer for you today. Not today. Yeah, we got to use the velocity and then plug in the time. Right, exactly. So my velocity equation is going to be negative 32 t. So if I plug in 6.124, I have no idea what you get.
Negative 195.
Sorry, I say that again. Negative 195.968. Good, okay. And we should label that, what are we in again? Feet. Feet per second. Okay. And see, what is the pebble's speed when it hits the ground? Yeah. I feel like that was too easy. Nice. Okay, the rest are yours. You guys have 10 questions. Not bad. Although that's more than we finished. Technically. Since you asked nicely. Oh, sorry. For my mistake. Who found it? Was it you? I'll give you one, because even though you made fun of me. Don't worry, it'll come around full circle. Never gonna live that down, damn it. Never give ammo. Let's see.